Hi everybody. I hope that you have had or are having a good fall break. And today we're going to talk about populations and ecology. So let's get started. First, we need a couple of definitions. A population is a group of individuals of a single species in an area. So a pride of lions living in a certain area of the savannah. A community would be a group of populations interacting with one another. So that includes other species. So all the lions, zebra, giraffe, wildebeest, everybody that's interacting in the area together. And within that community, we look at biodiversity. So biodiversity includes both species richness and the abundance of different species. So species richness is how many different types of species there are. So lions, elephants, giraffe, wildebeest, that would be four different species. The abundance of those species would be how many lions? 10. How many giraffe? 12. How many elephants? 20. And we use those in order to measure biodiversity. So, why do we care? The higher the level of biodiversity, the healthier the ecosystem is. The better able to function that ecosystem is. So, how do you measure biodiversity? Well, we came up with the Simpsons Index. And that is a really scary looking equation, isn't it? So, we're going to break this down, and it's not going to be so scary. Promise. I'm not a math person. D stands for diversity. Okay, we can do this. Little n is the number of individuals of a species. So the top has that little weird sigma, this little symbol, if you can see that. That just means add them up. So we're going to look at each species and how many there are. So I'll show you on the next page. And then how many there are minus 1. And then we're going to add all those up. Down at the bottom, capital N is the total number of all of the organisms. Total number of individuals of all the species together. And N minus 1 would just be total number of all individuals minus 1. Now, when we do all this math, our diversity can range from 0 to 1. The higher the number, the higher the diversity. So we want that number to be really high. So what you would do is make a standard size plot, rectangle or square, it's easier to measure. And let's say in our hypothetical plot, we have 3 species of animals. We find 10 mice, 1 roly-poly, and 3 frogs. So here is what this would look like. 1 minus the add them all up symbol. Okay. We had 10 mice, so the little n would be 10 for mice. Little n minus 1 for mice would be 9. You're going to multiply those. Next species, we have 1 roly-poly, and 1 minus 1 would be 0. So you'd multiply those together. The last species that we have are frogs. We had 3 frogs, so that would be our n for frogs. And then little n minus 1 for frogs would be 2. 3 minus 1 is 2. And then we're going to multiply those. Down at the bottom, we said we had big N. How many individuals? We had 10 plus 1 plus 3. That is 14 animals that we counted total. So that would be our big N. And big N minus 1 would be 13. We're going to multiply those together. So we do everything in the brackets first. So 10 times 9 would be 90. 1 times 0 is 0. And 3 times 2 is 6. Next, we're going to add these all up. But underneath, we have 14 times 13. Had to do that one on the calculator. That was 182. So we add all the top ones up, 90 plus 0 plus 6, and you get 96, divided by 182. That is 0.53. So when we have 1 minus 0.53, you get a diversity of 0.47. So it's below average, but that's okay. We want that number to be high, though. Couple more definitions. Habitat. Habitat is the area where an organism lives and reproduces. The ecological niche is the role a species plays in its community, and that includes its habitat, where it lives, and its interaction with other organisms. So there are two types of these niches. There's the fundamental niche, where a species can live if there's no competition, no predation, no resource limitations, so it's got unlimited food, no worries about predation, doesn't have to compete with anybody. That is its fundamental niche, where it could survive. The realized niche is where a species does live, because there's always going to be some kind of competition. There's always going to be some kind of predation, resource limitations in the wild. So I think I kind of skipped over it. The first exercise you're going to do has to do with measuring biodiversity. The second exercise you're going to look at involves this fundamental versus realized niche. So here's an example. This is, I can't even pronounce this, Chithamallus barnacles, that species, and the Balanus barnacles. So if there's no Balanus, none of these big Balanus barnacles, these Chithamallus, whatever, the sea barnacles, can live both in this low tide area and the high tide area. So that is their fundamental niche. However, Balanus barnacles compete with them for space, and they can live best in this low tide area, but they don't do really well in the upper area. So what really happens in the wild is you get this low tide area full of the Balanus species, and the sea species, because I can't pronounce the name, end up on the high tide area. But these Balanus outcompete them down here in the low tide area. So that was a competition for space. Species compete for all kinds of things. For habitat, which is the area they live, they compete for mates, they compete for food, the territory. That's kind of within a species. And when two species compete, the abundance of both species is negatively impacted. So if we go back, the species here is impacted because they can't live down here. But the Balanus is impacted because these guys outcompete them up here. So both have an adverse reaction. Now, intraspecies means within a species. Inter is like interstate, involves both species or more than one species. And they compete with other species for food, water, nesting area. And this competition occurs when organisms require the same resource, if they eat the same food, drink the same water, and that supply of the resource is limited. So if they have a huge lake to drink from, they don't necessarily have to compete for the water. If we're on a savanna in Africa where they have seasonal rains and temporary ponds, that might be a limited resource. Here are barnacles again. Both species could occupy the entire rock if the other species was absent. We call this the competitive exclusion principle. And that means no two species can indefinitely occupy the same niche at the same time. So, these guys do better at the bottom, these guys do better up top, and then there's this area in the middle where they really kind of fight for dominance there. One species will outcompete the other in this area of competition. Our next exercise deals with exponential growth, and that is a rate of growth population that increases exponentially, extremely rapidly. So, for population growth increases as the total number of females increases. Sorry guys, it doesn't matter how many males there are. And that's because females can give birth. So if you think about it, one island has 50 people, 25 males, 25 females. Another island has 100 people, 99 males, only 1 female. Which island is going to have the larger population growth? Yeah, the one with more females, because one female can only pump out so many babies. Exponential growth occurs when resources are unlimited, and there are phases to an exponential growth curve, which I will show you on the next slide. During the lag phase, growth is small because the population is small. Then you get the exponential growth phase, where growth is accelerating rapidly. So here we have this graph. Here's our lag phase. Population is slow, so we get kind of a slow start. And then you get this exponential. Area. So lag phase down here, exponential growth here. And it just seems like this is going to go on forever. But we run into environmental resistance. And that's all the environmental conditions that prevent populations from the maximum growth potential. So at some point, food, water, space, something's going to run out, and the population will be kept in check. We call this logistic growth. So after our exponential growth, we hit logistic growth. And that's when something slows down the exponential growth. There's not enough food, there's not enough water, there's not enough space. Every population must eventually come under some sort of environmental resistance. So here we have phases, the lag phase, the exponential phase. Then you have the deceleration phase, where growth begins to slow down and we hit an equilibrium. So we had that exponential growth right in here. We're slowing down, deceleration, and then we hit this stable area, and we call that the carrying capacity. Carrying capacity is the maximum number of individuals the environment can support. And the closer the population is to the carrying capacity, the greater the pushback from that environmental resistance. And we will continue this on the next video.